We will present here the structure of the full one-diode model and establish the equation corresponding to a real PV cell's behavior. We will illustrate the PV module equivalent circuit. Using this circuit, we will gradually build up the full one-diode model equation. Throughout this definition, we will define the series and shunt resistances and show their effect on the IV curve. The determination of the parameters of this equation will be the subject of the next presentations. You can recognize here the measurements of the IV curves of a PV module recorded at Sun. If we want to model this behavior for use in simulations, we must find a mathematical expression reproducing all these curves as best we can. We must construct these curves for any external conditions. That is, as a function of the two basic external variables, which are the irradiance and the temperature. This mathematical model is called the one-diode model. This may be represented by this equivalent circuit of a PV cell. We will present the equation corresponding to this model and give interpretations of the parameters of this equation. In the next presentation, we will see how to determine the parameters for any PV module. We have seen previously how to represent the photovoltaic effect with a diode and a current source. However, in reality, things are more complex. In the cell, there are additional phenomena which are represented by two parasitic resistors, which are the series resistance and the shunt resistance. The series resistance includes the bulk resistance of the materials used for the p-n junction, as well as the contact resistances between the different materials. In a module, there are also the connections between cells, named interconnections. You can see the effect of high series resistance on the IV curve in this plot. Series resistance affects the slope of the curve in the region of the open circuit voltage. We have also a shunt resistance in parallel with the diode, which will draw a little current due to current paths for the generated carriers to pass through. Shunts are typically caused by manufacturing defects. Unlike with series resistance, a higher shunt resistance is better for solar cell performance. You can see the effect of a low shunt resistance on the IV curve on this plot. Low shunt resistance affects the slope of the curve close to the short circuit current. Here is the equivalent circuit of the whole PV cell. The right part is the load that is using the produced electricity, represented as a single resistance. The main characteristics we have to determine are the voltage at the cell's terminals and the current drawn from the cell, represented in blue as V for the voltage and I for the current. Let's analyze the different elementary components of this circuit and build up the corresponding equation. We start with the currents in the circuit. Our load current I is equal to the photocurrent minus the current through the diode minus the current through the shunt resistor. Let's build up these currents one by one. The driving force of the circuit is the current source that represents the current generated by the photovoltaic effect. We can consider it as a pump of electrons. It produces the photocurrent, which we label IPH. This current is independent of the voltage. Some of this photocurrent passes through the diode, which is the basic p-n junction of the solar cell. We have seen previously with the Shockley equation that when increasing the voltage at the terminals of the diode, we have a current quasi-null at low voltages and suddenly growing exponentially with the voltage with a knee around 0.5 to 0.6 volts. We can evaluate the diode current I diode using the expression of the Shockley equation. This involves a factor named diode ideality factor, represented by the Greek letter gamma. NCS is the number of cells in series in case we are modeling a PV module. Don't mind about the details of this exponential. In the equation, this diode contribution is weighted by a parameter named diode saturation current, designated by I0, which is often referred to as I0. We will use V cell as a placeholder for the internal voltage of the cell, and this voltage is applied to the diode equation. The current across the shunt resistance produces a parasitic loss which behaves according to Ohm's law, for example, a current proportional to the internal voltage of the cell. Finally, in order to determine the internal voltage V cell, we consider the series resistance crossed by the output current I. This is also obeying Ohm's law. The series resistance produces a voltage drop proportional to the current, up to the terminal of the cell. This means that the internal voltage of the cell, V cell, is equal to the output voltage plus the voltage drop across the series resistance. Substituting this expression for V cell into the equation, we finally have the complete equation. The solar cell current is equal to the photocurrent minus current in the diode minus current in the shunt resistance. In conclusion, the one-diode model equation has two variables, namely load voltage and load current, which are our unknowns to be determined in blue. We have 5 unknown parameters in green that we need to feed to the measured data. These parameters describe the properties of a PV cell or module, and thus will be different for each type of PV module. Once they have been determined, the PV module can be described with the single diode model. And finally, we have several physical and external constants in black. In the next video, we will explore how we can determine these model parameters from a measured IV curve. As an introduction to the topic, let's look at the IV curve of a solar module. Here, you can see an example of an IV curve of a solar module. We can just notice that the IV curve of a solar module is identical to the IV curve of a solar cell with the voltage multiplied by the number of cells in series. Let's give an interpretation of different parts of the curve. Around the short circuit current, we have the current loss across the shunt resistance, which is proportional to the voltage due to the ohmic law. The slope of the straight line is the inverse of the shunt resistance. Then we have the current loss across the diode, represented by the exponential curve. Finally, we have the voltage drop across the series resistance, which is proportional to the current. This is also a straight line that follows the Ohm's law. Now we have established the full equation valid for a specific set of external conditions of irradiance and temperature, and we have to determine the 5 unknown parameters. We can do this using a single measured IV curve. This will be the subject of the next presentation. As an aside, outside of PVsyst, some people are using a more complex model called the two-diode model. This may be slightly more accurate, especially at low irradiances below 300 watts per square meter. The two-diode model is suited for research and work at the cell level, but the one-diode model accuracy is sufficient for our use in the study of full PV systems. The two-diode model involves more parameters which require more than a single IV curve measurement. Therefore, This model is unusable for the large database of PV modules in PVsyst.